3.3 Image formation due to refraction. Applications of refraction. You have learned the laws of refraction. Now you should know Snell's law. So light changes in direction when it travels across different media. For example, when a light ray travels from air to glass, it bends towards the normal, and therefore the angle measured in glass is smaller than that in air, so that the light ray becomes closer to the normal. So the reflected light will seem to come from a different direction, and an image is often formed. Let's use this idea to explain the following picture where there is a professor sitting inside a transparent water tank. The body of the physics professor moves to his right. Why is it so? Let's draw a ray diagram of W, X, Y, Z to explain. Now, a light ray from the body of the professor travels towards the glass surface and is reflected a lot when it enters air. The light ray bends away from normal as it travels towards the observer eye. If you draw two similar light rays in this way and produce the reflected rays backward, you can see the observer would believe that the light rays come from this point, which is the image of the object. In other words, an image of his body is formed on the right of his body. There are also other examples, as you will see on the next few pages. And always remember the following steps to locate image. 1. Draw two light rays from the same point of the object. 2. Draw the reflected rays. 3. Draw the virtual rays. 4. Locate and mark the image. Similarly, a fish always appears shallower. The side view looks like this. There's a fish, and its light goes to the surface of the water, reflected, and now goes to the observer eye. To locate the image, we have to draw two light rays, like this. Then draw the virtual rays by producing the reflected rays backward. So the observer receives the reflected rays, and he will believe the reflected rays come from here, which is the image of the fish. And now you can see the image is higher in position. It is shallower. Next is a well-known example. There's a coin in a cup, such that the observer eye just cannot see the coin. We know that by adding water, the observer can see it. But why? Let's draw a ray diagram to show what happens. We should draw two light rays, one by one, to the surface of water. Remember that the light ray always bends away from normal when it travels from water to air. And then a second light ray. Next, produce the reflected rays backward, like this. The observer will believe that the reflected light rays come from this point, which is the image of the coin. The observer can see the coin because there are light rays from the coin that reach the observer eye. Another example is a stick that is partially immersed in water. It will look bent. Yes, and if you don't believe it, you may try it at home. Put a chopstick into water partially in a big bowl. You will see it bend. Okay, but why it looks bent? Let's repeat the procedure to draw the image of the stick and the water. So we draw two light rays from X, the tip of the stick, 1 and 2. We produce it backward to find the intersection point to locate the image. There you are. So Y is the image of X. And so where is the whole image of the stick and the water? It should be like this. As part of the stick out of water has no change. That's why it looks bent. Distorted vision due to refraction. There are also examples in nature. A archerfish eats insects on tree branches. It jets out a stream of water to the target bug, and the bug will fall into water easily. When the bug is directly above an archerfish, the light ray does not bend, and the archerfish may locate the bug easily. However, usually the bug is not directly above the fish. When the fish sees underwater, the light ray from air bends towards normal. So inexperienced fish cannot locate the bug accurately. However, after some time, an archerfish starts to learn from experience, and it will adjust the direction of its water jets and target the bug more accurately. Similarly, the great blue heron also have the same problem. When they try to find food underwater, the refraction of light also makes them miss their target prey easily. So many great blue herons learn to look perpendicularly into water to find the little fish or shrimp as their food. 3.4. Refraction and speed of light. On page 34, we have learned that refraction is due to change in speed of light in different media. So how fast is the speed of light in different media? Light travels at the highest speed in vacuum, but light travels slower in other media such as water and glass, as given by the following formula. So the speed of light is related to the refractive index of the medium. Now let's take the speed of light in vacuum to be 3 times 10 to the power 8 meter per second, and find the speed in other media. In water, for example, the speed of light should be found like this. That is 3 times 10 to the power 8 divided by the speed of light in water equals the refractive index of water 1.33. In that case, the speed of light in water is found to be 2.28 times 10 to the power 8 meter per second. You can easily notice that the speed of light in all other medium is smaller than that in vacuum. So that's why the refractive index of all other medium are greater than 1. 3.5. Refraction by rectangular block and prism. In both cases, there are two refractions when the light ray passes through the rectangular block or prism. In question 35, we have seen how light ray pass through a rectangular block. The incident ray and the emergent ray are parallel, but it is laterally displaced. The lateral displacement increases with the angle of incidence, the refractive index, and the size of the block. (3.5.2) Refraction by prism. When a light ray passes through a prism, it bends towards the normal when it enters the glass prism, and the light ray bends away from normal when it emerges from the prism. In this way, a light ray always bends towards the base of a prism. Every time when the light ray bends, the light ray changes in direction. First, by angle d1 in the first refraction, and then by angle d2 in the second refraction. So altogether, the angle of deflection is d1 plus d2. 3.6. Dispersion of light. For some medium, such as glass, the speed of light depends on the frequency of light. In other words, different colors of light travel at different speeds in glass. We call it dispersion. When a ray of white light enters a prism, different colors of light bend differently. Red is deflected less, while violet is deflected more. In other words, refractive index of red light is smaller. As different colors of light emerges from the prism, they are deflected one more time. So they are deflected twice. And different colors of light are separated even more from each other. We say that white light is dispersed into different colors. It forms a color spectrum.